Hi, and welcome to the 12th lecture of Introductory Astronomy. We were off last week, so this week we're back, and we're going to go out into the galaxy. We're going to start exploring the rest of the universe. So, however, first, before we do that, we have to go in and study the center of our solar system, because it's a more typical object of the rest of the universe, the least part that we can see, which would be our own sun. So today we're going to be doing the sun's atmosphere, and on Wednesday we're going to be doing the sun's interior. But I'll let you in a little secret that I'm actually going to tape these one after the next. So both of these tapings will be done on Monday, so people should not try to come to class on Wednesday if you're out there. I'm going off to a scientific meeting. So not only, most astronomers are research astronomers, so like many professors at this university and most astronomers, I participate in different aspects of research, and so I'm going off to present some research and to learn about what other people have been doing in one of my subfields. So anyway, things to contemplate are, what is this puffball doing? What is that? And I guess it's not so hard just to know what it is, but as to how you're seeing it. Okay, so first the obligatory slide. This is PH 1600. This is lecture 12. Next time we'll be talking about the sun's interior. This is being taped at Michigan Tech. I am this professor, and if you're taking the course for credit, you need to go to this website. What does it say? Information is free, but t-shirts cost money. In this case, it's not just t-shirts that cost the money, it's actually getting credit for the course that costs money. But the information is free and has always been free. Well, not always, because astronomy changes, but you could always go to the web and learn this stuff, or go to the library and learn this stuff. I just provide a way of learning it more quickly. So, if you're taking the class for credit, you're responsible for the lecture material as spoken by me, except for my mistakes, which hopefully I will correct, so you just have to listen to see what those mistakes are. You're also responsible for certain Wikipedia entries, but not the higher math there. Basically, the ideas there. You're responsible for all the astronomy pictures of the day that are posted during the semester. And I will review these once a week. So this week, Tuesdays and Wednesdays haven't been created yet. So I can only review up to Mondays, and then next week we'll go back and review a couple extras. So homework quizzes 1 through 6 should have already been completed. The midterm should have already been completed. I've looked at many of the midterm grades. They are generally pretty good. There was particularly one concern that my mistake in that in question 3, there were 2 correct answers, and only one of them was giving a correct answer. One was listed in centimeters and one was listed in kilometers. So I'm going to go back and investigate how to change that so you'll get credit for both centimeters and kilometers for that one. So if you answered it correctly, either way, you will get credit. It might not show up right away, but it will show up before your final grade is calculated. So I will create, before leaving the next quiz and release it on Wednesday, just like the next lecture will be released on Wednesday. The only thing that will seem different is that there won't be anybody sitting here, and I'll strangely be wearing the same sweater. Okay. Talking about the sun, so to be clear, the Wikipedia entries you're responsible for are the sun, sunspot, solar cycle, and facula. To answer a common concern, when I talk about this with other people, people worry that how can you give questions based on Wikipedia, because someone could just go in and change Wikipedia to match their answers. So right now, the more industrious people who've taken the midterm and wanted a perfect grade are now changing the Wikipedia entries to match their grade and will demand full credit very soon. Well, a couple of things. You'd have to go back and edit my lecture, so you need to find a lookalike of me and retape me and dub it on top of me. That's one thing you need to do to get credit. Another thing is you need to go back into the past and change the Wikipedia page as it appeared in the beginning of this semester, because I'm not that stupid. I am aware that people could change Wikipedia pages, so I won't just be checking if you claim that Wikipedia has been changed, the latest page. I can go back, and as you might know, Wikipedia keeps a history of all its pages. And I will be seeing whether it was changed, just your answers, and who's changing them. So I advise not changing the Wikipedia pages to match your midterm answers. Okay, so how do we study the sun? Well, the sun has been noticed for a really long time. It's one of those things that are so obvious that it's not actually reported in papers. There's a lot of research still being done on the sun, but the existence of the sun predates recorded history. We wouldn't be here unless the sun existed, specifically. However, in modern times, I would not advise looking at the sun because that would burn your eyes out, and you would have a really good view of an overexposed sun for a fraction of a second before never seeing anything again. There are special observatories, for instance, the Solar McMath Observatory on Kitt Peak. So this is Kitt Peak National Observatory you see here, and I think this is the 4-meter Mayall Dome, and there are lots of telescopes on Kitt Peak, all of them smaller than Kitt Peak, than this Mayall. But here we see the solar telescope, which job is to look at the sun and things that are generally too bright for other telescopes like Venus. So they don't have optics that can melt or CCDs that can melt. And the sun's image goes down this long enclosure there, my understanding is. Okay, so what do we know about the sun? Well, typically the sun is visible during the day. Some of you may have noticed this yourself. It's generally not visible during the night. Also, we sort of know it's up during the day even if clouds are in front of it because other people report it. Based on a survey of nearby stars, it turns out the sun is clearly the closest star. So close it gives us warmth, significant warmth. The sun turns out to be a relatively normal star. It is not a super bright star. It is not the brightest star in the stellar neighborhood. It is not the dimmest star in the solar neighborhood. It's relatively normal. It's about halfway through its life. It's been going for billions of years and will go for billions of years more. The sun is, because of its stability, possibly it helped life develop on Earth. So the sun isn't drastically changing its brightness by factors of 2 on the time scale of days, weeks, or months. It's pretty constant. That's small, well within a percentage over times that we could have measured it. The sun orbits the center of the Milky Way galaxy. Lots and lots of stars in the Milky Way galaxy, billions, one might say, hundreds of billions, 10 to the 11th or so. Not a particularly interesting star. Sometimes we're in a spiral arm, sometimes we're not. It takes well over 100 million years, I think it's on the order of 200 million years, for the sun to go about the center of our galaxy. So it takes a year for the Earth to go around the sun, but it takes about 200 million years for our sun to go all the way around the center. Really long time, but still, since the sun is billions of years old, it's done that a whole bunch of times. So we've been round and round the center of our galaxy. Other fun facts about the sun is it's mostly hydrogen gas. The next element after that would be helium. As we know, helium was discovered on the sun, and I'll mention that again later. So the sun has somewhat, we can guess what the elements were in the beginning of the universe, and that was mostly hydrogen and helium. And the sun has mostly hydrogen and helium. The sun has trace amounts of other elements, though, including carbon, xenon, all the elements that are on the Earth are at least the same amount in the sun, but they're so much diluted by the hydrogen and helium that we see that it's hard to identify them, but they're there. The sun actually has a lot of what's called metals, which are any element heavier than helium, than we think it should have if it was created from the very early primordial gas of the universe. So we think the sun is not a first-generation star. We think the sun is a second or possibly third, more probably third-generation star. So way back in the early universe, and we'll do the early universe. We're going to go there. You're going to be there. You're going to see the early stars form. Just hang with me. We'll see the early stars form, and they will explode in spectacular supernova explosions after creating some heavy elements, some metals in their core. Then other stars will form. That were population 3 stars. Population 2 stars would form, of which we see a lot in our galaxy, particularly in globular clusters. And so many of those stars will disperse in some way, many of them going supernovae, and again put back more heavy elements into the gas around the galaxy than before. It is out of that gas that already has a lot of relatively heavy elements that the sun has formed. So the sun would be in a population 1 star. With these heavy elements and the solar nebula, we can then have things like planets form, because the Earth is made out of all these metals, these heavy elements. Lots of things that are much heavier than hydrogen and helium, like water and carbon and things that make up rocks that the Earth is made out of. So these only happened on Earth relatively recently. So dinosaurs walked hundreds of millions of years ago. Life has developed a few billion years ago. We'll have a thing on life. But the sun has been around 5 billion years, and the Earth has been around almost as long. So we've seen this twice, so why not show it again? This is the solar spectrum. So the sun does not only emit one color. The sun doesn't emit the yellow color that it seems to be. The sun emits all different kinds of colors. Every color across the visible wavelength that we can measure. So here's a spectrum, which you can get by passing sunlight, or any light, but particularly sunlight, it's fun, through a prism, which is a triangular piece of glass many times. And here's some of the red light that's broken out. Here's some of the blue light. The sun is actually somewhat yellow. Now, I had indicated before the sun is green. And the sun is green in the sense that it's more green than we can see. Because the blue light of the sun some of the blue light of the sun is taken out by the Earth's atmosphere, which is why the rest of the sky looks blue. But I got a bunch of email, particularly from people who weren't registered for the course, who are watching around the world, who pointed out web pages that say the sun is not as green as I was indicating. The sun's color is actually pretty yellowish. But it is true that it is more green than we see, because it is true that a lot of the blue light, some of the blue light is being scattered out. Now, here we see dark absorption lines that we discussed earlier in the course. Many of them are due to relatively cooler elements, atoms, molecules in the solar atmosphere. So these things, they look dark in this frame, but they're not completely dark. They're still there. It's just that there's relatively less of it than colors right around there. So this is how we can tell the sun has a lot of hydrogen in it. Although there's many elements. This helium, as we know, was discovered on the sun. We saw some of these lines. We said, what are those? And we figured out that there must be an element related to the sun that was then later found on Earth called helios for the sun. It's called helium. And most of the other lines here we can identify with atoms and molecules of some type, but not all of them. We don't know what all of them are yet. Still working on some of them. Okay, so what about the sun? How big is it? The sun is big, 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 big. It is 104 Earth diameters big. So as I'm fond of saying, if your Michigan Tech engineering enterprise is to throw the Earth into the sun, you would not affect the sun very much. You would affect the Earth greatly. The Earth would just totally dissolve and be mixed in with solar elements, not significantly increasing all the elements the sun has. Still, the sun would be predominantly hydrogen and a little bit of helium. It would not increase its diameter much at all. It would not become 105 Earth diameters if we threw the Earth in there. It would be 104, which is actually an estimation plus a tiny little bit. Okay, so the sun has 330,000 times the mass of the Earth. So it's way, way, way more massive than the Earth. So again, throwing the Earth in there, putting it up, I rounded it off. There's actually numbers there. But they weren't important because I rounded it off, because I don't think it's important to try to memorize numbers that don't really give you the scale of what's going on anymore. But whatever that number was that I rounded off, add 1 to it if you threw the Earth into it. Now, the Earth spins as a solid body, which means that the poles and the equator spin at the same rate, but not the sun, because the sun is pretty much gas. You can't land on the sun. The sun doesn't have a solid surface. The sun is a big gas ball. And eventually, the gases become so dense that electrons get bounced around, and they can't be held onto by protons anymore. And when electrons and protons separate, it becomes opaque to light, because light likes to bounce off of. Light, being electromagnetic radiation, likes to bounce off of the protons and the electrons. So when that happens in the photosphere of the sun, we can't see in there anymore. And we consider that to be the surface of the sun. But if you tried to land on it, you'd melt well before you hit anything you thought of the surface. So there are no missions designed to land on the sun, because that would be silly. The sun rotates 26 days at the equator, 36 days at the pole. At the photosphere, which is the last surface that we can see, the sun's temperature is about 5,800 kelvins. So Kelvin is a unit of temperature. similar to Celsius in that 1 degree of Kelvin, one change of degree of Kelvin is equal to one change of degree of Celsius, but they have different 0 points. So 0 degrees Kelvin is much colder than 0 degrees Celsius. 0 degrees Celsius is designed to be when water freezes, but that's like 270 or something like that, or is it 260 degrees Kelvin. So it turned out that they found a new 0 point that you can go down to. They like to define 0 as the coldest things can get. So previously people thought that freezing water was the coldest you can get. So let's call that 0. But then they thought, oh, no, you can get down to where molecular speeds diminish to near 0, and that would be 0 degrees Kelvin. And now, of course, we have effectively negative temperature. Lasers have negative temperature. But we don't redefine temperatures anymore. So 0 degrees Kelvin is still defined dynamically. The average density of the sun is a little higher than that of water, which makes it higher than that of Jupiter and Saturn, because Jupiter and Saturn have an average less density than water. So if you had a bathtub big enough, the sun would sink and Saturn would float. It wouldn't actually sink, though. It would be very strange putting it in a tub of water. Strange chemical things would happen, and there would be loud explosions, I think. But if you think of the thought experiment, it wouldn't float. It would sink. Okay, so here is a thing happening off of the sun. This is an explosive erupting solar prominence here. Lots of pretty pictures today. The sun is a very photogenic object, particularly its outer part. Next lecture, not so many pretty pictures, but a lot of pretty pictures today. The sun is a churning, interesting mess. Strangely enough, it almost all averages out, so we get just about the same amount of sunlight all the time. Here's our dinky little Earth right here compared to a prominence on the sun. So compared to the mass of the sun, the stuff in here is almost nothing. Doesn't affect things. If you were to take the Earth and you were to put it here, it would be really annoying for satellites, but it would not destroy life on Earth. So this is very thin gas here. So here you see, we'll have more pictures of the sun and we'll show more what's happening. Okay. So the sun's atmosphere is typically divided into at least 3 components. The part that we can see, the surface we can see down to is called the photosphere. And on the photosphere we see stuff. It's not a completely uniform sun we see. We see sunspots. Again, you shouldn't look at this directly, but sunspots have been noted by taking little pinhole cameras, taking a sheet, putting a hole in it, and then putting another sheet behind it. You can see an image of the sun, and you can see if there are sunspots or not. You don't need a telescope to see sunspots. So sunspots have been noted pre-telescope times. With a telescope, you can see sunspots even better. There are other things. The sun is actually divided up into areas we'll see called granules. So the sun is sort of like tiled. And each tile is called a granule. And as I'll discuss, these granules come and go on the time scale of hours, typically. The sun, besides sunspots, typically around sunspots, an active region has faculas. Sometimes if people are keen on the Greek, they put an E here for the plural. But I find that confuses students more than anything, so I put an S there to anglicize the plural of facula to faculas. They are typically the bright regions that surround sunspots. The sunspots are typically somewhat cooler than the surrounding photosphere, being held down by the magnetic field of the sun, where faculas are hotter. So temperature on the average, though, is still about 5,800 degrees Kelvin. Above the photosphere that we see through is the chromosphere. The chromosphere has other things. It has filaments in it, it has prominences, it has coronal mass ejections, it has spicules, which we'll talk about. And the temperature at the top of the chromosphere is about 10,000 degrees. Outside of that, there is the corona. The corona has holes in it. It is a very low density, and it is very hot. And it is one of the major pushes in astronomy major mysteries in astronomy to try to figure out, why is the corona so hot? One would think that as you went away from the sun, that you would get further away from the nuclear fusion that occurs deep in its core. And as the sun cools, as you go out from the core, it gets cooler and cooler, then you hit the surface, which is the photosphere, and then as you go up past that, it should get yet cooler again. But it does not. The sun gets hotter. Here we see it's 10,000 above the photosphere, and it goes over 1,000,000 degrees in the corona. And so we think we understand, we don't understand the details as to why, but we understand that there is probably magnetic processes that are causing it. Exactly how these magnetic processes are causing it, we don't know the details. Okay, relatively recently we can see, well, it's been known that the sun has flared for a while. When the sun flares, it throws off a tremendous amount of particles into the solar system, and these particles can hit the Earth. So what do we care? Well, solar flares have actually damaged, they push on the magnetic field of the Earth and cause changes in the magnetic field, and that can cause power grids on the Earth to change and to fail. Also, as we'll see images, the particles that stream out from a flare can hit the Earth. And so our atmosphere, though, protects us, so we're going to be fine. It changes the magnetic field, but we don't really care about the magnetic field unless we're plugged in, unless you have a compass, it might slowly flicker, although I actually haven't heard of a case of that. It can, as I said, hurt the power grids. But what it can do, it can knock out satellites that are above the Earth and don't have the atmosphere of the Earth to protect them. So theoretically, your cell phone could go out if there's a big solar flare. When a solar flare leaves the sun, it creates an outgoing quake that has been only seen relatively recently. It has been hypothesized before that, but this is an outgoing disturbance, like an earthquake. Okay? And here we see an image of one going out, a large tsunami. So here is some kind of solar event, probably a flare. So I'll go previous and next, and we'll see it again. And you can see this huge thing going around the sun. Tsunami. It's not related to the tides, so I'm reluctant to call it a tidal wave. Tsunami, I think, is a better word. All right. People have been watching the sun, not directly for many, many years. Hundreds of years have been recorded. So they've noticed that the sun goes in cycles. And one of the main cycles is a magnetic cycle, which we now takes 22 years. But it appears to take about 11 years. There's 11 years between solar maximum and solar minimum. During solar minimum, there's not much going on in the sun. Like right now, and as I've reported in a few APODs, there is surprisingly little activity on the sun. There is only rarely a sunspot recently. Relatively few flares. So now it's a good time to be an astronaut because astronauts can be affected by flares. Not only might your cell phone go out, but as astronauts are afraid of flares, there's a big flare, they can get hit by a lot of radiation, and it's like being X-rayed a bunch of times. That's not good. Lots of radiation is bad for humans. So every 11 years, it appears, we know it's now two changes of polarity that cause 22 years, the sun undergoes a maximum. So several years ago, although they're not 5.5 years apart, the sun was on the average, a lot of sunspots, a lot of flares, a lot of coronal mass ejections. So the solar minimum that we're in started around 2006 and appears to be ongoing today, although we think now that we're starting a new solar cycle. Okay, so here's the sun in ultraviolet light. Excuse me. Here we see the sun. I think it's probably taken, although this APOD was posted in 2006, I believe the sun is of an earlier time when it was near maximum. There's a lot of active regions. In an active region, you will find sunspots, you will find faculas, you will find these things here. Here you can see there's lots of charged particles moving about on the sun. These charged particles tend to move along magnetic field lines, and these magnetic field lines loop. So why do charged particles care about magnetic field lines? Well, as you know, you can, an electric field will accelerate an electric charge straight away. But a magnetic field, you can move along a magnetic field line if you're a charged particle for free. It doesn't take any force to push yourself. You can just glide along a magnetic field line. But to move across magnetic field lines takes force. So given that there's no force around, the things that charged particles are typical to do is to just follow the field lines and they will arc. Therefore, you see lots of arcs that go. The sun's magnetic field is very complex, much more complex than the Earth's. There's many places, sunspots are places where the magnetic field pokes through the sun. It's not a simple dipole like on the Earth. There's lots of places where it goes, magnetic field lines go into and out of the sun. Okay, so here you see a sunspot region. Here you see dark sunspots. This is called the umbra of the spot, sort of like an umbra of an eclipse. And the part around it is called the penumbra, just like similar to an eclipse, but there's no eclipsing going on here. There's just the dark and less dark regions. These are facula. Faculas. That's an F. So these regions are darker, are brighter than the surrounding sun, and these are darker. So here, there's less, due to these are depressed into the sun, and there's not as much activity going on in these regions, so they're cooler. Here, there's much more activity going on, and so they're slightly hotter than the rest of the sun. If you were to take one of these sunspots, though, and move it off the sun, it would be tremendously bright. So we're just talking about a difference of, a few degrees. So it's still going to be 5,000 degrees hot. It's going to glow. Okay, here's a relatively isolated sunspot. Here you can see it in wavelengths that show you higher and higher above the sun. So you can see yourself moving into the chromosphere. So this part here is the umbra. This part here is the penumbra. And this sunspot is roughly the size of the Earth, which is superimposed for fun. When you see the facula, you can see that there are tubes, essentially, that move around the sun, that show above the surface of the sun where the different charged plasma will be moving. So let's try that again. Here you can see in the beginning, you can see the granules on the sun, too. Okay, this is a sunspot seen sideways. Sunspot region seen sideways. Here you can see it's a very energetic place. There's lots of, we'll see several images like this. Lots of plasma being catapulted off the sun and then gliding along magnetic field lines. Here's one of the closest images yet of a sunspot. Really see a lot of detail. Again, here's the umbra, here's the penumbra. This was taken with a vacuum tower telescope, a powerful Earth-based telescope that can see the sun. Currently, I'll mention there's actually 3 satellites that are looking at the sun. They don't have the angular resolution that the Earth-based satellites do, unlike the Hubble Space Telescope, which has a lot of angular resolution. The 3 satellites that are orbiting the sun near the Earth are SOHO, Hinode, 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 and Stereo, which is actually 2 satellites. But none of these 3 took this image. Here you can see granules. Here's a granule. Okay, here's a particularly interesting image of sunspots. It shows that they're not all just these circular things. They're sometimes complex regions. Here are light bridges that connect 2 different parts over a sunspot. So there's plasma in this tunnel, in this bridge. Here's another surface that it's actually seen somewhat from the side, so you can see some surface relief. You can see the sun is not perfectly spherical. It has raised and depressed regions. Typically, the sunspots are the depressed regions. The granules sometimes are slightly higher than other parts as the gas rises and falls. Okay, so now here are 2 cool movies. Let's see if they've been loaded. We might have to wait for these to load. Both of them were pictured on Picture of the Day. So let's go to the first one. Okay, does it need to load again? No, it's already loaded. So this is a really cool image. I really like this image a lot. Let's see if I can. This is a time lapse of what it's like to look near a sunspot. And you can just look at this many times in succession. Maybe I'm strange in that I like to look at it. You can see the granules here evolve, and it takes them minutes to evolve. So this over here, I keep playing it again, will show you the amount of minutes, and you can see some sunspots come and go over the let's see, is it hour that this thing takes? 54 minutes. You can see how the sunspots change themselves over the time scale of an hour. Very illuminating for seeing how the sun changes. Okay. So now let's look at the next one, which might be even cooler. Okay. Let's click here, scroll down. Okay. Yes. All right. So here you see a clock here. So again, it takes on the time scale of an hour, and you can see an active region. Actually, things explode off. You see things explode and falling back. Particularly if you watch this, there's a fountain there. So I just won't say anything, as you can watch the tremendous amount of solar activity over the time scale of, I guess it's a few minutes. So the sun might appear to be a relatively constant object to us, but if you go right up to the surface, there's a tremendous amount of violent things happening on the sun. Okay, so let's minimize that one if it wants to go. Doesn't always want to go. Okay, let's minimize that one and go back to the lecture already in progress. Recent evidence, particularly by the SOHO satellite, has shown that the sunspots we see are not the total story with the sun. There's lots of tiny little dark and bright areas where typically the bright areas are where, they're where magnetic fields come out of and go into the sun. So the dark areas are relatively cool, the bright areas are relatively hot, and there's lots of them all over the sun. And in a sense, the sun has a carpet of these things. Okay, one of the things we're finding out now is that the sun is changing over. It's going through solar minimum, and the next solar cycle is beginning. It is thought that possibly the first sunspot of this new solar cycle was seen in 2006, but that's now, I think, somewhat disputed. And so we'll look now at this one. There was an astronomy picture today just in September 2008, and this is possibly the second region of the correct polarity. So here's the sun. You can see in this color, you don't see the individual granules so much as just different regions around there. You can see some prominences, which we'll look at more in detail. But here is an active region that has been just seen in September that hadn't been. Active regions are somewhat absent. You've had tiny little ones, but nothing this big for a while. So we think the next solar cycle is starting up, and it's been unusually quiet minimum, solar minimum, and a very unusual solar minimum. I haven't seen a solar minimum like this for 50 years or more. So here we plot the number of sunspots as a function of year, and these go back to near the year 1600. So here you can see every 11 years there's a maximum and then there's a minimum. Maximum, minimum. So right here, well, 2006, 2008, there's an unusually wide and deep minimum. It does not yet rival something called the Maunder minimum, which occurred between 1650 and 1700, when they had the ability to see sunspots because they were seeing them here and here. But they just didn't see solar maximum. So the sun, as recently as, 400 years ago, 350 years ago, did something strange. Now, I don't think this was dangerous to life on Earth. There was life. There were people back in the 1600s. So it didn't have that big an effect. But the sun and its magnetic cycle is not completely understood. We don't know what caused the Maunder minimum. We don't know if another one would come up. I think there were some people who were sort of worrying that we were entering one now. But I think now the sun is showing more and more spots, so we don't think we're in a Maunder minimum, something like a Maunder minimum. So here's a graphic of all the way from 1996 to 2006, images in the ultraviolet, where you can see the bright active regions more clearly. In 1996, it was not very active. It became more and more active every year. And so 2001, I think, was solar maximum. The sun, it doesn't always look like this in 2001. It goes from less than this to more than this, but this is somewhat indicative of what the sun looked like. And then it decreased as the years went by to 2006, all the way to 2008, when we've had a broad and deep solar minimum. Okay, here you see another picture. This one was taken by the TRACE satellite. Actually, I think TRACE is still looking at the sun. TRACE is up there too. I forgot about that. So here is an active region. An unusual active region. This is a solar filament lifting off the sun, so we'll look more at filaments. It's an unusual filament in that It's not a simple loop. Many times on the sun you see simple loops where plasma will rise and fall in this loop. But here you see something more strange. Sometimes there can be figure eights or other things. We don't completely understand the dynamics as to why material lifting off the sun has that shape. Okay, these are spicules. So we're seeing that, I think, a higher energy. So you're seeing higher on the sun, and you can see these things are like flux tubes going from different regions. In particular, this is a sunspot region to active regions. And so when you look at the sun at slightly higher energies, you see, and you zoom in on the sun's surface, you see all these tubes of high energy plasma moving around. And it's a little bit like a carpet. Looks like the sun is carpeted with these plasma tubes. The sun's magnetic field here, the sun is much smaller than you can see. These are tubes of constant magnetic density. So it looks like a tube. So constant field lines, plasma again will flow on those tubes. Inside of that might be a tube of slightly higher magnetic field. Okay, so here you see a filament here. A filament can appear as a slightly dark region. This is because the filament is actually lifted above the sun. Here you see one too. This is stuff filaments can last a month or so. They are hovering above the sun. And when they're seen off the edge, they're like this, they're known as prominences. And there's been some really cool pictures of prominences off the edge of the sun. Relatively cool gas held up on the time scale of month by the sun's magnetic field. So here's one. Isn't that cool looking? This stuff is just sort of hovering there. It's not that thick. Sunlight goes through it. We're not going to be eclipsed if this goes between us and the sun. No. When it goes between us and the sun, we just see a slight region like this. Typically, when the sun is showing lots of filaments, the sun does not appear darker, though, because to counterbalance the filaments, there's these brighter regions. There's faculas around the sun. Typically, when the sun is active, it's slightly, but just slightly brighter to make up for all the, if you include both faculas and the sunspots in the filaments. So here you see a spectacular filament. This is nothing. It's cosmic ray hit on the detector. Here you see one moving out from the sun. So the Earth may be about this big. It could easily fit in that. It is an unusually shaped filament. It's one of these figure eight ones. It looks like a claw. That's why I like it. I put it on APOD a few times. A claw moving out from the sun. Okay, here is a picture of a coronal mass ejection. So these come out of the corona through weak spots in the corona out into the solar system. They're happening a lot of the time. They're less energetic than flares. This is a particularly interesting shot from the SOHO satellite because here the sun is hidden behind this disk. This is an opaque disk in there. The sun would actually be right there inside that circle, but we don't see the sun directly. What we do see is coronal mass ejection moving out, and this was taken at a time when you can actually see a bunch of planets. Here's Saturn, there's Jupiter, there's Venus, there's the Pleiades star cluster in the background, and even Mercury. So it's a very active region here. This was taken in, I think, very far into the ultraviolet. It's very more blue than we can see, near solar maximum, or a time when the sun was very active, 2003. So you see lots of active regions here, and you can see some not so active regions right there. So here's a coronal mass ejection, and you can actually see a comet in the same field. So that was a pretty cool catch. You can see a bright comet and a coronal mass ejection in the same field. Okay, this is a nice color image. You can see the sun in deep ultraviolet light only. You can see its dark and bright regions, and off of it you can see a coronal mass ejection here. And you can even see stuff coming off the sun in other directions. But this big area here, which will create a cloud that will move out. When this cloud hits the Earth, it will cause, if it were to hit the Earth, they don't necessarily all hit the Earth, it might cause auroras. So we're constantly watching for flares and coronal mass ejections to see if that cloud of particles moving out in the solar system hits the Earth and causes auroras. Here you see this, 3 different images of the sun. One is the sun taken by one of the orbiting satellites that can actually look at just the sun. So here you see the sun and its granulation and an active region. Now, soon after this was taken, the sun underwent a total eclipse of the sun, and so we can see the corona, which you can see in the solar eclipse. And then you can see past the occulting disk, you can see what was going on outside of the corona just a few minutes later, and you can see there is stuff streaming off the sun that does match up reasonably well with the coronas. This is a tremendous solar flare that came off the sun, and what's interesting about this is you can see that the particles from the solar flare hit the detector and cause all this graininess, which is why it's not good to have satellites orbiting. I mean, you can't avoid them. Why satellites are vulnerable to solar flares, and why one of the important things is we cannot really predict when a powerful solar flare will occur, but it is one of our goals is to understand the sun well enough to know that a powerful solar flare is coming. To save our satellites, to protect cell phone coverage, to save our solar grids, not only our solar grids, but our electric grids that would change with the magnetic field of the Earth, and also to protect astronauts. Almost always these days we have an astronaut up there, usually now in the International Space Station, sometimes with the space shuttle, or there's other countries that now routinely launch astronauts. Not only Russia, but now China has launched astronauts, and India, Japan are working toward that. Another image, so here's the corona, again, one of my favorite images of the sun. This was taken from the South Pole. And in all the line are the sun far in the distance, which you can't see the photosphere of because it's being blocked by the moon, which is this. So here we have sun. This is corona. Here you have person. And then behind right here is photographer, who's taking this picture. Sorry, it's hard to read. So there's four things all lined up. The bright sun, a moon, a person observing it, and a photographer behind that person. So there's actually two people. Two heavenly bodies, two people. Here again is the corona. We know a lot about the corona from the orbiting spacecraft and also from during total eclipses of the sun, when the corona becomes very clear. Here is the corona, sometimes called the crown of the sun. Okay, coming off the sun is the wind from the sun. So even now, when the sun is at solar minimum, we don't see lots of activity. There's not lots of coronal mass ejections, very few, almost none. Not lots of solar flares, but still there's magnetic activity on the surface of the sun, and there's still particles escaping from the sun. So the sun is very slightly losing mass as stuff comes out from the sun. There is a wind coming off of the sun. And we've seen evidence of this wind in previous images. When this wind sweeps, when a break in the wind sweeps past the tail of a comet, it can totally break off the tail of a comet, particularly the ion tail. But here we see, out here is the wind. And this wind is constantly hitting things out in the solar system. It's hitting comets, it's hitting the Earth. The further out you go, the thinner it is. The solar wind can go 400 kilometers per second. I think that's the slow part of the solar wind. There's even a higher solar wind out there. But the densest part goes around 400 kilometers per second out and can vary depending on what's going on the sun. Okay, other things about the sun. We have two satellites at least that are in the outer solar system. There's also two Pioneers. But the ones that are tracked the most that we can still track are the Voyagers. And they're moving out past something called the termination shock. So this is not a photograph. This is a illustration, which reminds me that we're actually, just today, the IBIS satellite was launched, which is successfully launched, which will study these things in more detail. So in a few years after the satellite has been gaining data, we should know more about everything I'm talking about today, particularly with regard to the termination shock, the heliosphere, the heliopause, the heliosheath, and the bow shock than ever before, thanks to IBIS, assuming it works as it's supposed to. So about 90 astronomical units from the sun, where the Voyager 1 is now. It's, let's see, not my field, so looking at some details here. The Voyager, so the termination shock, inside the termination shock, if I understand correctly, that's the fluctuating boundary of the solar wind. So the solar wind ends pretty much on the termination shock. So I would guess that would move around some. At the heliopause, the solar wind and interstellar gas begin to mix. Here's the heliopause. Outside of that, the sun's motion, the heliosphere's motion through the interstellar medium creates a bow shock in front of it. Here's the bow shock. I believe inside the heliosheath is the area that's dominated by the sun. Most of the particles would be solar particles. There. So here we see another image, the heliosphere and heliopause. So let's see. The solar wind, the surface where the solar wind drops below sound speed is called the termination shock. Okay, so now I know that termination shock. So the solar wind is going beneath sound speed at the termination shock. Okay, I got that clear. Okay, so the actual contact sheet between the sun's ions and the galaxy's ions is the heliopause. And that occurs at 110 AU. So we can see that here. It's the heliopause here. And I believe that is here. This is the heliopause. And I believe this is the, what's called here, the bow shock. This is the bow shock. So as our sun moves through the interstellar medium, it creates a shock, and there are regions where the particles you'll find are dominated by the sun's particles, and those are labeled here. Inside of this, where we live, right near the sun, we're dominated by the sun's influence. And almost all stars have things like that. Okay, so with that, I will leave us off with the sun's atmosphere and solar wind for today. And so next lecture, we will be reviewing the interior of the sun. Actually, I'm going to jump off into another aspect called gravitational lensing, because I didn't have any place really to put it in the course. Then there, fits in well there. And I will be reviewing the astronomy pictures of the day back to the last one that was discussed next lecture, which for you will be released on Wednesday as usual, but I will record in just a few minutes. So I'll see you next time. Bye.